Good morning. This is your Stat Sensei, Mr. Spensei, and this is Death Packet on chi-square and regression. This will be problems 51 through 60, focusing primarily on regression. A certain cell phone plan charges a fee of $1 for each international call made, plus 2 cents for each second of talk time for the international call. So basically, the price equals $1 plus 0.02 times the number of, I'll use S for seconds. So that's our equation line. All right. A business owner to track the time and cost for each of the calls made by the employees when they travel internationally for business. What is the appropriate value of the correlation? Well, in this case, they said it equals this. So if I have a 1 second call, it's a minute and it's going to be $1.02. All right. Regardless what I put in there, this is going to be exactly what I have to pay. So this model right here is a perfect model. I know exactly what I'm going to pay. If I make a 10-second call, it's going to be 1 plus 0.02 times 10. If I make a 20-second call, 1 plus 0.02 times 20, etc. And because I know it, because this is what I'm going to pay, because it doesn't vary, my correlation is perfect, which means, oh, and my slope is positive. So I have a positive slope. The longer my call, the more I pay. So I have a line like this, and every single point is going to lie on that line. So as second increases, my money will also increase. So because this is a perfect correlation, that means the appropriate value is 1 because we have a perfect linear relationship. Kind of rare, but happens sometimes, especially if we're working with equations. All right. Workers at a warehouse of consumer goods gather items from the warehouse to fill customer orders. The number of items in a sample of orders and the time and minutes it took the workers to gather the items were recorded. A scatter plot of the recorded data showed a curved pattern, and the square root of the number of items was taken to create a linear pattern. All right. The following table shows the computer output from the least squares regression analysis created to predict the time it takes to gather the items in order. Based on the regression output, which of the following is the predicted time in minutes that it took to gather the items if the order has 22 items? All right. So we have a constant. So this is basically our equation. Y hat equals 3.0979 times, or excuse me, plus 2.7633 times the square root of n, where I'm going to say n is the number of items. Okay? So with that said, let's do this. We have 3.0979 plus 2.7633 times, we have 22 items, 22 raised to the half power. And the half power is the way I do my square root. I end up getting 16.05. All right. So 16.058. My closest answer is B. So 16.06. Please notice the key is they said that they're taking the square root of the number of items, and they tried to let us know that there. So that was my equation. Okay. All right. 53. In baseball, two statistics, the earned run average and the walks and hits per inning pitched, are used to measure the quality of pitchers. For both measures, smaller values indicate higher quality. The following computer output gives the results from predicting ERA by using WHIP in a least squares regression for the 2017 baseball season. Okay. Which of the following statements is the best interpretation of the 6.8? All right. So this is my slope. Okay. So I'm going to write my equation. My equation is basically ERA because that's what we're predicting, equals -5 plus a positive slope of 6.8 times WHIP. So that's essentially my equation there. All right. So if that's my equation and they want to know what is the best interpretation of 6.8, that's my slope. And remember, in this case, it's always y over x. So there's my y value. This is my x. So we have a 6.8 and it's positive. So this is a 6.8 increase in ERA for every one increase. And it's remember, it's always one in width. So ERA is predicted to increase by 6.8 units for each unit increase in WIP. And that's 1, 6.8, 6.8, 1. And we have the Y's in our correct response. So we're predicting this to increase by 6.8 for every 1 unit increase in WIP. So 53 is A. All right, 54. Researchers are investigating the amount of monthly rainfall measured in centimeters, how it affects the monthly growth of a certain plant. From a sample of data, the researchers created a least squares regression line. Computer output is shown in the following table. Which of the following statements is an interpretation of 0.75? All right, so 0.75. That's my y-intercept. Matter of fact, if I were writing my equation, we're looking at, what are we looking at? Rainfall and growth. So we're going to say uh, rainfall, or excuse me, growth equals 0.75 plus 0.15. I'm going to put R for rainfall because I don't have enough room to write it out. Okay. So this is my y-intercept. And my y-intercept means that x is 0. So when we'd expect to, if we had no rain, we'd expect to have a 0.75 growth. All right. Monthly growth is expected to increase by 0.75 when rainfall increases by 1. No, that would be 0.1. If that's that would be using the slope definition, which would be 0.15. As rainfall increases by 1, we have a 0.15 increase in growth. Rainfall is expected to increase by 0.75. No, not rainfall. We're talking about growth. For a month with 0 centimeters of rainfall, the monthly growth is expected to be approximately 0.75. All right. Um, I like this one. Let's keep reading because we have another one with 0. For a plant with 0 centimeters of monthly growth, no, it's not monthly growth, it's monthly rainfall. For 0 centimeters of rainfall, the monthly growth is expected to be approximately 0.75. Our best answer is C, because this would be, oh, if this is 0, that goes away. Growth is 0.75. 55. A regression analysis was conducted to investigate the relationship between the total charge and travel time for a certain car service. Computer output from a linear regression analysis is shown below. The analysis is performed on a sample of 24 observations. Assume that the conditions for inference for the slope of the regression have been met. Which of the following defines the margin of error of a 90% confidence interval for the slope of the least squares regression line? All right. So 24 observations. Well, degrees of freedom is going to be very important in this. So degrees of freedom is going to be n minus 2. So degrees of freedom is going to be 24 minus 2. All right. So, and um, our formula is basically, I'm going to use B for my slope, plus or minus T star times standard error. Well, we know our standard error is 0.23. Looks like we have a little bit of a typo though. So we know we're going to have a 0.23. And all we're looking for is the margin of error, which is this part right here. So we need to calculate our T star. All right, so there's a typo here. So this is going to have to be one of either D or E. All right, this should have been either that should have been 0.023 or this should have been 0.23. But let's calculate our T star. So second vars, inverse T, parenthesis. We want a 90% because that's what they said here. So 1 minus 0.90, close parenthesis, divided by 2, degrees of freedom are the sample size minus 2, 24 minus 2. And I get 1717. So my 1.717 times, and the one that has that is E. So the answer to 55 is E. Continuing on, 56. A restaurant manager collected data for the number of customers in a party in a restaurant and the time elapsed until the party left the restaurant. The manager computed a correlation of 0.78 between the two variables. What information does the correlation provide about the relationship between the number of customers in a party at the restaurant and the time elapsed until the party left the restaurant? Okay, so it's a positive relationship. So it's a positive relationship, and it says between the number of customers. So as the number of customers go up, the time elapsed, time goes up. And we know this because it's positive, so they both have to move in the same direction. All right. The relationship is linear. No, we can't say that. The only way we can tell if it's linear is from a residual plot. The relationship is not linear. Once again, we can only tell that from a residual plot. The parties with a larger number of customers are associated with longer times elapsed. I'm kind of liking that one. All right. So that looks pretty good. Let's keep going and see if there's anything better, but that looks like it to me. The parties with a larger number of customers are associated with a shorter. No, more customers, longer time. There's no relationship. No, we definitely have a relationship. All right. So best answer for 56 is C. Computer output for a least squares regression analysis based on a sample size 17 is showed on the table. Okay. Assuming all conditions for inference are met, which of the following defines a 95% confidence interval for the slope of the least squares regression line? Well, remember, it's basically B plus or minus T star times the standard error, all right? And a standard error of the slope. And B represents the slope. So first off, my slope is 5.65 plus or minus. We'll come back to T star in just a moment. We know our standard error of the slope because we're just going to look down the slope row is 1.14. So we need to calculate T star. All right. Well, to do that, we need a 95%. So we know that. We also need to know our degrees of freedom. And our degrees of freedom are going to be n minus 2. So 17 minus 2. So second vars inverse T, parenthesis 1 minus 0.95, close parenthesis, divided by 2. Degrees of freedom in this case are 17 minus 2. And we get 2.131 times 1.14. All right. So, well, wouldn't you know, C and E have both the same answer. All right. So that's a problem. So we're going to go with the one that occurred first and say that this one is an error. All right. So we're going to go with C, but this is the way you do it. All right. And both of those had the same answer. Sorry about that. 58. The number of students taking AP statistics at a high school during the years 2000 2007 is fitted with a regression line with the least squares. The graph of the residuals of some of the computer output is as follows. How many students took AP Statistics in the year 2003? Well, first off, this is the year 2003. So when I look at the year 2003, I find I have a residual. And here's all right, if I'm above the line, I have a positive residual, so I have a positive of 5. So let's go ahead and write our equation and make a prediction as to what we expect. So what we expect is, um, and it's supposed to be the number of students. So I'm just going to use it for y hat as the number of students equals my constant 11 times, or 11 plus 13.9826 times the number of years. All right. Well, that's going to be y hat equals 11 plus 13.9826 times 3. So that's 52.9478. So y hat equals 52.9478. That's what we predicted. All right, that's our predicted. So remember, a residual equals the observed minus the expected. All right, or the actual minus the predicted. Well, we know our residual is 5 because we calculated that up here. We don't know what our observed is. So we don't know what our observed is, but we know that our expected was 52.9478. So if I add 52.9 to both sides, I end up getting 5 plus 52 is 57.9. All right. Well, we don't have a part student, so we must have observed 58, right? So 58 is our observed or our actual. Best answer to 58 is E. All right, moving on to 59. A real estate agent wants to predict the selling price of single-family homes for the size of each house. A scatter plot created from a sample of houses shows an exponential relationship between the price in thousands of dollars and size in 100 square feet. To create a linear model, the natural logarithm of price was taken at the least square regression line and was given the natural log of price equals 2.08 plus 0.11 times the size. Based on the model, which of the following is closest to the predicted selling price for a house with a size of 3,200 feet? All right, I'm sorry about pausing that. I left off a decimal place. I was working on solving this and was not getting a reasonable answer. So I left off the 2.08. So our equation is basically the natural log of price equals 2.08 plus 11 times the size. But they said the size is per 100 square feet. So we're going to take the 3,200 and divide it by 100 and we get 32. So we have the natural log of price, ln of price equals 2.08 plus 0.11 times 32. So let's solve that first. All right. 2.08 plus 0.11 times 32 is 5.6. So we need natural log of price equals 5.6. I need to raise that to e to the x because that's the way you undo the natural log. So this is going to be e to the 5.6. So second, the natural log, and then raised to the 5.6, e to the 5.6. So we have an exponential. We have 270.426. 270.426, but they said in thousands of dollars. So I need to come back and multiply that by 1,000. When I do that, my closest answer is going to be B because I'm going to get about $270,426. All right. Number 60. A small business owner has created a linear regression model to predict the number of new customers who will visit a shop based on the number of times the owner has an advertisement played on the radio. What is the explanatory um, and what is the response? So they're asking me for what my Y and what my X is. So let's reread that. All right, to predict the number of new customers. So this right here, predict the number of new customers, or the number of new customers, that's going to be my Y. That's going to be my response based on the number of times the owner has advertisement. So number of times the owner has the advertisement, this will be my X, and X stands for explanatory. So explanatory, number of new customers? No. Explanatory, number of times the advertisement is played? Yes. Response to number of new customers. I like that. Explanatory, number of times the advertisement is played? Response to number of purchases. They didn't ask about the number of purchases. They asked the number of new customers. Explanatory, number of purchases? No. Explanatory, number of previous customers? No. So our best answer to 60 is B. All right. Appreciate you watching and look forward to seeing you on the next one. Thank you.